In this video, we're going to review momentum and impulse. Momentum is the product of mass times velocity. The equation is P equals mv, P for momentum, v for velocity, and both momentum and velocity are vectors, so you'll see those vector arrows on the top. So for example, object 1 on the left would have a momentum of 5 kilograms times 2 meters per second, which gives us a momentum of 10 kilograms meters per second. And object 2 would have a momentum of 10 times 1 meter per second, which also gives us 10 kilograms meters per second. However, if we were to make right positive, object 2 would have a negative momentum. So interesting to notice here is that these two masses are different. The object on the right has twice the mass, but yet because it has half the velocity, they both have the same momentum as far as the magnitude, but the direction is going to be different. One has a positive momentum and one has a negative momentum. Next, we're going to define impulse. Impulse is defined as the net force times the change in time. Sometimes you use the symbol J, sometimes you'll see the symbol I, both meaning the same thing. If you're given a graph, we can use the area under the curve of the force time graph to find the impulse. So in this graph, we can use the average net force. So even though it's got kind of a curve shaped here, if you know the average net force, you can use the average net force times the time, and that would also give you, so 2 times 4 here, and we get 8 Newton seconds, and that would be the impulse. So if you're given the graph, remember you were looking for the area under the curve. If on your graph you have both a positive force and a negative force on the force versus time graph, then we need to take into account that there's going to be a positive and a negative area. So here we're going to have a positive impulse, and here we're going to have a negative impulse. And in this situation, the areas are going to be the same. So the impulse on the system is going to be 0 because it's going to cancel out. Remember that impulse is also a vector because net force is a vector, impulse is also a vector here. Now we're going to connect impulse with momentum by starting with Newton's second law, which is the net force is equal to ma. And we know that acceleration is delta v over delta t. And if I move the delta t to the left-hand side, I get the net force times delta t is equal to m delta v. And we can rewrite this, we can expand this to write mv final minus mv initial. So what this is telling us is that the impulse on the left-hand side here, the impulse force net times delta t is equal to the change in momentum, right? Because F net delta t is impulse and mv is momentum. So we can rewrite this as I, or impulse, is equal to final momentum minus initial momentum. You can also write it as impulse is equal to the change in momentum. And the key thing here is this relationship right here, right? Because what this is telling us is that if you have an impulse, you're going to change the momentum of the object or the system that you're working on. And this relationship is called the impulse-momentum theorem. Here's an application of the impulse-momentum theorem. Here we have a truck that is going out of control and has a choice to stop by running into a pile of hay or to a concrete wall. And as you know, that the pile of hay will be safer than the concrete wall. But how does the impulse-momentum theorem help us to analyze this? Well, we're going to assume that both trucks are moving at the same speed before they slow down. And so when they slow down to a stop, they're going to both have 0 momentum. They're not moving. So they both have the same change in momentum. Doesn't matter how they slow down, they're both going to slow down to a stop, so they have the same change in momentum. The difference, though, is that with the hay, you have a longer stopping time, And the concrete wall, you have a shorter stopping time. And the trade-off, and here's the trade-off, is you're going to have a smaller force on the hay, and on the concrete wall, you can have a bigger force. So same change in momentum. However, because the stopping time is less on the hay, is greater on the hay, so it's going to have a smaller force. And this is why airbags are helpful, because the airbags in a car extends the stopping time and thereby decreases the impact force on the passenger. The impulse momentum theorem is super helpful if in our system we can set up a system where there are no external net forces acting on it. And if that is the case, then the impulse is going to be zero because there's no external net force acting on it, and impulse is net force times time. Then that means that the change in momentum is going to equal zero. And the change in momentum is equal to zero. I can move my initial momentum to the left, which tells me that the initial momentum of the system equals the final momentum of the system. And if there are more than one objects, then we can say that P1 plus P2, the momentum of object 1 plus the momentum of object 2, is equal to the moment of object 1 prime. That means for me it's going to be after, maybe it's a collision or sometime later, plus the momentum of P2 prime. So this here is called the conservation of momentum, and it's super helpful if you can set up your system such as there is no external net forces, and we call this type of system an isolated system. Next, we'll look at some situations where the momentum is conserved. When we say that momentum is conserved, we're saying that the initial momentum equals the final momentum. But we have a special case called an elastic collision. In this case, both momentum and kinetic energy are conserved. Here we have a situation where one cart, which has twice the mass as the second cart, is traveling towards the right at a velocity v1, bumps into object 2, which has zero velocity, and then after they bump into each other, the second cart starts to move, and then the first cart continues moving towards the right. So in this situation, the initial momentum is going to be 2mv1 for object 1, and object 2 is not moving, so it's going to be 0, is equal to after the collision, object 1 has a momentum of 2mv1 prime plus mv2 prime. So the conservation of momentum allows us to be able to write down this relationship here as far as momentum is concerned. But because it's an elastic collision, that means the kinetic energy is also conserved. Kinetic energy, as you'll remember from our energy unit, is 1 over 2 mv squared. So the initial cart on the left will have a kinetic energy of 1 over 2 times 2m, because it's got twice the mass, times v1 squared. Object 2 initially will have 0 kinetic energy because it's not moving. And then after the collision, the first object has a kinetic energy of 1 over 2 mv1 prime squared, and object 2 will have a kinetic energy of 1 over 2 mv2 prime squared. And so both of these statements are going to be true, and it's going to be kind of a pain because you do need to do a little bit of algebra. I'll link on the corner here some shortcuts that you can use for elastic collision problems. In an inelastic collision, momentum is conserved, but kinetic energy is not. So using our equations from the previous example, we can say that the equation on the left here, the total initial momentum, is equal to the final total momentum. However, as far as energy is concerned, they're not going to be equal. The total energy initial is going to be greater than the total kinetic energy final, and because some of that kinetic energy is lost or leaves the system. I don't like to use the word loss. It doesn't disappear. It leaves the system through, sometimes it could be through heat or sound. So whatever the case, or deformation of the carts, so whatever the case, there's going to be less kinetic energy after the collision than before the kinetic energy, because you have some energy that's leaves the system through heat or sound, etc. Now we have a situation where the objects stick together after the collision, and we call this a perfectly inelastic collision because momentum is still conserved, however kinetic energy is not conserved. And so before the collision, we have the momentum of the two cart, the first cart that's traveling, bumps into the second cart, which is initially at rest, and afterwards they stick together. So afterwards, their momentum, you can treat it as with this one large mass, one large object. So we just add up the masses, 2m plus m times the final velocity. And then we can simplify this to 2m v1 is equal to 3m v prime, or v final there. You'll notice that the m's in this case, they cancel out, which leaves us with 2 over 3 times v1 is equal to v prime, or v final. So the final velocity of this two-cart system is equal to 2/3 of the initial velocity of object 1. The nice thing about solving a perfectly inelastic collision is that the objects are moving together, and then so that you can just deal with one final velocity rather than two different velocities for each of the objects. So now we're going to take a look at a situation called an explosion, and this is another case of inelastic collision where the object breaks apart but the total momentum is conserved. Here we have two carts, and in between the cart is a spring which is going to push them apart. Initially the momentum is 0, so I'm going to put 0 on the left hand side of my equation. On the right hand side, after they explode, they're going to move apart from each other. So object 1 will have a momentum of 2m v1 prime. Object 2 will have a momentum of m v2 prime. You'll notice that the masses cancel out, and then we can kind of move one of these values to the left. So we have 2 v1 prime is equal to v2 prime. And so now we have a nice little relationship. Oh, this is going to be negative because one's going to be moving to the left, one's moving to the right. And so now we have a nice little relationship. The nice thing about this type of problem, explosion, is that initially, that if they're not moving, we could just set it to 0. However, they could still be moving initially. And even if they're moving initially, the momentum will still be conserved. Conservation of momentum also works for two-dimensional motion. Momentum will be conserved in each direction independently as long as there's no external impulse in that direction. So here we have a ball hits another ball. Object 1 is initially moving, object 2 is initially not moving. They hit each other, and then they bounce off in their respective kind of directions here. So let's think about this in the x direction. I'm going to make horizontal direction the x direction. So in the x direction, initially, object ball 1 is moving towards the right, and we're going to use the horizontal velocity. It's only moving horizontal, so it would just be its v1, and set that equal to, and object 2 is initially not moving, so it's 0, and then set that equal to the mass of object 1 times the velocity, the final velocity of object 1, times cosine theta. And the reason we do cosine theta is because we're analyzing just the horizontal direction here, the x direction here, and then plus the mass of object 2 times velocity 2 prime times cosine theta 2. And cosine theta 2, once again, is because we're looking at the horizontal component, or the x direction component of v2. So what we're essentially saying here is that the net momentum in the x direction initially is equal to the net momentum of the net momentum in the x direction after the collision. That's essentially what we're saying. And then vertically, we can see the same thing except for the y direction, so that the net momentum in the y direction is equal to the net momentum in the y direction after the collision. And you can see that initially in the y direction there was 0 momentum, so that's going to be on the left, is equal to, and we're going to use sine theta here because now we're looking at the y component or the vertical component of the velocity. For a more mathematical analysis of these type of two-dimensional momentum problems, check out the video in the top right corner. Now we'll take a moment to think about the center of mass. Center of mass sometimes can be super helpful and almost like a shortcut in solving some physics problems. The center of mass is the average of the masses factored by their distance from a reference point. So the center of mass position is equal to m1x1 plus m2x2 divided by the total mass. And I've got some examples of some different shaped objects. I've got a square, center of mass would be right in the center there. I've got a donut, it'd be right in the middle, which tells us that the center of mass does not have to be on a location on the object. It could be in space. And then I have kind of a irregular shape here. So you can think of the center of mass as kind of where you would, how you would balance. If I had to put this on a little pivot thing to balance it, that's where I would balance it. Also, what you could do is you could hang a piece of string, and where if you continue that string all the way down and hang another piece of string over here, and then where it stops rotating, then where those dotted lines intersect, that is also your center of mass there. Okay, so here I have a classic walking on a boat or walking on a plank problem. So as this person is moving towards the right, what's going to happen to this boat, and how far is it going to move? Well, as this person moves towards the right, the person is pushing back on the boat, and so the boat is going to move towards the left. Now let's think about this in terms of the center of mass. Center of mass is right here for the boat, and for the person it's going to be right there approximately. And then so the center of mass is going to be somewhere in between those two, depending on which has more mass. So let's say that the center of mass is right there, and so the person moves to the right. As the person moves to the right, the boat moves to the left. However, one thing we know for sure is that the center of mass will stay along this dotted line here as long as there's no external net force, no impulse acting on our system. Which means that however much this person moves towards the right, the boat will move to the left in such a way that the center of mass of the boat person system will still lie along this dotted line here. So the big idea is that if there are no external net force on the system, the center of mass will stay at rest if it was already at rest. And if it was already moving, then it will stay at constant velocity. This reminds us of Newton's first law. So now let's take a look at a center of mass problem. We've got a block on a wedge, and the wedge is on a frictionless surface. And so the question I want to ask is, as the block is sliding down, will the direction of the center of mass, first of all, will it be moving, and what direction will it be moving? And if it is moving, is it going to be accelerating? Is it going to be moving at constant speed, or is it going to be speeding up? And so let's take a look at this problem. So first of all, we're going to make our system. Our system is going to be the block and the wedge. So horizontally speaking here, there's no external net force. So since there's no external net force, we would expect that the center of mass to not move horizontally. So let's think about the center of mass here. The center of mass of the block is there, the wedge is here. So horizontally, it's going to stay along this line. So the block will move down, it's going to move to the left. The wedge, therefore, means it would have to be moving towards the right to maintain that center of mass so that it is staying along that vertical dotted line right there. So we're saying that the center of mass velocity is going to, in the x direction, is 0 because the net force, horizontal net force in our system is 0. However, what about vertically? Well, vertically, the center of mass is actually moving downward because gravity is an external net force vertically and pulling the block down. So vertically, the velocity increases downward, And this is because the net force in the y direction is downward. So this kind of reminds us of Newton's second law, that if you have external net force, you're going to have an acceleration.